After months of anticipation, NASA finally released the images. 12 spacecraft, multiple telescopes, all pointed at the same interstellar visitor. But here's what nobody expected. Each one saw something different, and we're not talking about slightly different angles or minor variations in clarity. We're talking about observations so fundamentally distinct that when scientists first compared them, they were surprised by the variety of what different instrument types revealed. How is that even possible? How can 12 separate missions, all observing the same cosmic object during the same window of time, produce results that look like they captured completely different phenomena? This isn't supposed to happen in modern astronomy. Our technology is precise. Our methods are refined. When we point instruments at a target, especially one as significant as an interstellar visitor, we expect consistency. We expect the data to align, to confirm what we're seeing, to build a unified picture. Instead, what NASA received was a collection of images and data sets that seemed to contradict each other. Some spacecraft captured what looked like a fuzzy sphere of light, glowing but indistinct. Others detected invisible chemical signatures that revealed hidden molecular activity. One mission saw barely anything at all, just a faint smudge against the backdrop of space. And when these observations were laid out side by side, the differences weren't just technical, they were profound enough to make even seasoned astronomers pause and reconsider what they thought they understood about observing objects from beyond our solar system. Stay with me. In the next several minutes, we're going to walk through exactly what each of these spacecraft saw, why their observations differed so dramatically, and what those differences actually tell us about how we study the universe. We'll examine the Mars orbiters that achieved the closest views, the asteroid explorers that somehow captured details from impossible distances, the solar observatories that track this visitor through regions of space where Earth-based telescopes are completely blind. And we'll address the question that's been circulating since these images were released. Do these contradictions mean something more than just technical variations? When 3I Atlas was identified as the third confirmed interstellar object in human history, astronomers understood they had a rare opportunity. These visitors don't come often. Before this, we'd only confirmed 2 others, and both had passed through too quickly for thorough study. So NASA made a decision that had never been attempted at this scale. They mobilized everything. Every spacecraft with a line of sight, every telescope that could be repositioned, every camera that might catch even a glimpse. This wasn't just about taking pictures. This was about turning the entire inner solar system into one massive observatory, coordinating assets that were never designed to work together, all focused on a single target carrying secrets from another star. But then, the government shutdown happened. The images were delayed by a government shutdown that affected NASA operations. When the shutdown ended in mid-November, NASA moved quickly to share their findings. Speculation grew online during that silence. People wondered what those images might reveal. Rumors circulated about anomalies, about observations that didn't match standard comet behavior, about findings that contradicted expectations. The delay only intensified the curiosity, the questions, the theories about what NASA might be seeing. On November 19th, the wait finally ended. NASA unveiled their collection of observations, and what they showed was both stunning and bewildering. Because while the images themselves were remarkable, what struck everyone immediately was how different they were from each other. This wasn't a matter of one spacecraft getting a better shot than another. It was about fundamental differences in what each mission detected, how they interpreted the same object, and what story their instruments were telling. And that's when scientists realized something important. This campaign wasn't just about studying an interstellar comet. It was revealing something deeper about observation itself, about how the tools we use shape what we see, about how perspective and method and technology all combine to create understanding that's far more complex than simply pointing a camera. So hit that like button right now if you're ready to dive into one of the most fascinating observation campaigns in modern astronomy. Drop a comment telling me which spacecraft's view you think captured the most crucial information, because as we go through each one, you'll see that every observation told a different piece of the story. And by the end, you'll understand why those differences aren't a problem to be solved, but a revelation about how science actually works when we're studying something truly unprecedented. Let's begin. When NASA uses the word unprecedented, they mean it. This isn't marketing language or exaggeration. Unprecedented means it has never happened before, and in the case of 3I Atlas, that statement is absolutely accurate. 12 NASA spacecraft and telescopes, all redirected toward a single target, all capturing data simultaneously as this interstellar visitor made its journey through our neighbourhood. Think about what that actually required. These missions weren't built to collaborate. They were designed with specific purposes, specific targets, specific scientific goals that had nothing to do with tracking a comet from another star system. Mars orbiters study Mars. They map the surface, analyse the atmosphere, search for signs of ancient water. Asteroid missions travel for years to reach distant rocky bodies, their instruments calibrated for close examination of mineral composition and geological features. Observatories watch our sun, tracking solar flares and coronal mass ejections, monitoring the constant flow of energy that sustains life on Earth. None of these missions woke up one morning expecting to become part of a coordinated effort to study an interstellar object. But when 3i Atlas appeared, everything changed. Mission planners started recalculating trajectories. Engineers began reprogramming instruments that had been operating in routine mode for months or years. Scientists from completely different fields found themselves coordinating observation windows, sharing data, building strategies together. This level of coordination doesn't happen casually. It requires approvals, resource allocation, technical adjustments, and willingness from multiple teams to temporarily set aside their primary objectives. Why would NASA go to all this trouble? The answer is simple and profound. Because opportunities like this almost never come. Interstellar objects are extraordinarily rare. Before 3i Atlas, humanity had confirmed only 2 others in all of recorded history. The first, Oumuamua, arrived in 2017 and vanished before we could properly study it. We caught it too late, realised what it was too late, and watched it disappear back into the darkness of space with most of our questions unanswered. The second, 2i Borisov, showed up in 2019 and gave us slightly more time, but even that window was limited. Scientists studied it as thoroughly as they could, but they were left wanting more data, more observations, more chances to understand what makes these visitors different from objects born in our own solar system. So when 3i Atlas was discovered, NASA decided they would not let this opportunity slip away. They would mobilize everything available. Every spacecraft with a clear line of sight would be tasked. Every telescope that could be repositioned would participate. Every camera capable of capturing even a faint signal would be activated. This wasn't about getting one good image. It was about gathering as much data as possible from as many perspectives as possible, knowing that the next interstellar object might not arrive for years or decades. The coordination itself was staggering. The Mars Reconnaissance Orbiter had to rotate away from its primary mission of imaging the Martian surface, pointing its powerful camera toward a target millions of miles away. MAVEN adjusted its observation schedule, using its ultraviolet instruments to capture wavelengths invisible to human eyes. Down on the Martian surface, the Perseverance rover aimed its cameras skyward, attempting something it was never designed to do: astronomical observation from ground level on another planet. Far from Mars, the Lucy spacecraft was millions of miles into its journey toward Jupiter's Trojan asteroids. Psyche was travelling through the asteroid belt, heading for a metal-rich target years away. Both missions paused their routine operations, turned their instruments backward, and captured observations of 3i Atlas from distances that seemed almost absurd. Observing a comet from that far away is like trying to photograph a candle flame from across an entire state. The light is faint, the target is small, and every technical challenge is magnified by sheer distance. Even solar observatories joined the campaign. Stereo, SOHO, and the newly launched Punch mission all track the comet as it passed through regions near the Sun where Earth-based telescopes simply cannot see. This was particularly crucial because during late September and early October, 3i Atlas moved through a blind zone from Earth's perspective. Without these space-based solar observatories, there would have been gaps in the tracking data, periods where scientists wouldn't know exactly where the comet was or how it was behaving. And what did scientists expect from all this coordination? They expected consistency. Sure, different instruments would capture different wavelengths. An ultraviolet camera would see things an optical camera would miss. Resolution would vary based on distance and instrument design. But the fundamental structure, the basic characteristics, the object itself that should remain recognizable across all observations. Comets are comets, after all. They have a nucleus, the solid core of ice and rock. They develop a coma, the cloud of gas and dust that forms as sunlight warms them. Many grow tails, streams of material pushed away by solar radiation and solar wind. These features might look different depending on your viewing angle, your instrument type, your distance from the target. But they should still be identifiable. That was the reasonable expectation. That was what decades of comet observation had taught astronomers to anticipate. But when the images started coming back, when scientists began comparing what each spacecraft had captured, something unexpected emerged. The observations weren't just different in quality or clarity. They were different in fundamental ways that made scientists question whether some standard assumption about observation was missing from their models. Each spacecraft was seeing 3i Atlas differently. Not variations of the same view, but genuinely distinct representations that emphasized different aspects, revealed different features, told different stories about what this object actually was. And scientists were starting to understand that this wasn't a problem to be solved when astronomers started asking not just what they were looking at, but why their tools were showing them such varied results. This wasn't a failure of technology or coordination. It was the beginning of a deeper understanding about how we observe the universe, about what it means to study something from multiple perspectives, about the relationship between our instruments and the reality they're designed to measure. But before scientists could fully grasp that insight, they had to work through each observation, understand what each spacecraft had actually detected, and figure out why those detections seemed so incompatible at first glance. The Mars spacecraft had the closest views, and their observations would become the foundation for everything that followed. The Mars spacecraft had the best seats in the house. In early October, 3i Atlas passed within what astronomers call striking distance of Mars. That's still millions of miles, but in astronomical terms it was close. Close enough that NASA's 3 Mars missions, orbiting and working on the red planet, could turn their instruments toward this visitor and capture some of the most detailed observations anyone would get during the entire campaign. The Mars Reconnaissance Orbiter had been circling Mars since 2006, carrying a camera called HiRISE, the High-Resolution Imaging Science Experiment. HiRISE is extraordinarily powerful. On Mars, it can spot details smaller than a dining room table from orbit. It has captured thousands of images of the Martian surface, revealing avalanches as they happen, tracking dust storms, identifying potential landing sites for future missions. Its resolution is remarkable, its precision proven over nearly 2 decades of operation. So when MRO rotated to point HiRISE at 3i Atlas on October 2nd, expectations were naturally high. This was going to be one of the closest views any spacecraft would achieve. The comet was approaching from a favourable angle, and HiRISE had the technical capability to resolve details that other cameras might miss. Scientists hoped they might see structure in the coma, possibly even glimpse the nucleus itself despite the surrounding cloud of dust and gas. What HiRISE actually captured was a pixelated white sphere, not a crisp image showing fine details of the nucleus, not clear structure revealing how the coma was organised, just a fuzzy, pixelated ball of light where each pixel represented roughly 30 kilometres. Scientists could clearly see the bright inner coma, the region closest to the nucleus where dust and gas are densest. But the nucleus itself, estimated from other observations to be just a few kilometres across, was completely invisible at this resolution. It was too small, too deeply buried in the surrounding material, too faint compared to the bright dust reflecting sunlight around it. There was another complication. During the exposure, MRO experienced what's called spacecraft jitter, tiny vibrations that are almost impossible to eliminate completely in space. Normally these vibrations don't matter much because HiRISE is photographing a stable surface beneath it. But when observing a distant point source like a comet, even tiny movements smear the image across multiple pixels, blurring details that might otherwise be visible. The result was an image that showed 3i Atlas was there, that confirmed its brightness and general size, but revealed far less detail than hoped. Shane Byrne, HiRISE's principal investigator, acknowledged what they learned. Observations of interstellar objects are still rare enough that every attempt teaches something new. This particular observation taught them that even from Mars, even with one of the most powerful cameras ever sent to another planet, capturing fine details of an interstellar comet's nucleus remains extraordinarily difficult. The coma extended beyond HiRISE's entire field of view. They were only capturing the brightest central region, and even that appeared as a pixelated sphere rather than a detailed portrait. But just days earlier, another Mars orbiter had been watching 3i Atlas with completely different eyes. MAVEN, The Mars Atmosphere and Volatile Evolution mission doesn't carry optical cameras. It studies atmospheres and particles using ultraviolet light, wavelengths invisible to human vision. And starting September 27th, MAVEN turned its imaging ultraviolet spectrograph toward the comet, capturing something HiRISE never could: the chemical composition of the material streaming away from 3I Atlas. What MAVEN saw looked nothing like HiRISE's pixelated white sphere. The ultraviolet images showed glowing regions of hydrogen, maps of hydroxyl molecules, chemical signatures that revealed what the comet was made of and what it was releasing as sunlight warmed it. This wasn't about structure or appearance anymore. This was about chemistry, about identifying the specific molecules present in the coma and understanding what they meant. Shannon Curry, MAVEN's principal investigator, described the images as incredible. The detections they were seeing were significant, and they had only begun to analyze what the data revealed. MAVEN captured hydrogen streaming away from the nucleus, hydroxyl forming as water molecules broke apart under solar radiation, and early estimates of deuterium ratios that could help trace where 3I Atlas originated. Justin Deegan, MAVEN's deputy principal investigator who led the comet observations, talked about the moment they first saw their results. There was adrenaline, he said, the rush that comes when you realize you're measuring something no one has measured before. Every observation opened new understanding about how interstellar objects behave, what they're made of, how they compare to comets born in our own solar system. But here's what becomes immediately obvious when you place these observations side by side. HiRISE showed a bright, pixelated sphere with no chemical information. MAVEN showed chemical maps with no structural detail. Both were observing the same object at roughly the same time from the same planetary orbit. Yet their images are so different that if you didn't know better, you might think they were looking at completely different phenomena. One told a story of light and shape. The other told a story of molecules and composition. Neither was wrong, but neither was complete. Down on the Martian surface, Perseverance rover attempted something even more ambitious. On October 4th, it pointed its Mascamzid camera toward the sky and opened the shutter for an exceptionally long exposure. Perseverance wasn't designed for astronomy. Its cameras are built to study rocks and soil, to help scientists understand Martian geology, to search for signs of ancient microbial life. Pointing those cameras at a moving object millions of miles away through Mars's thin atmosphere, with no ability to track the target during exposure, was a technical challenge that pushed the equipment beyond its intended purpose. The comet appeared as a faint smudge, barely perceptible. The stars in the background streaked across the image because Mascamzid couldn't track their motion. It's a fixed camera attached to a rover sitting on Martian dirt, not a precision astronomical instrument. But Perseverance captured it. From the surface of another planet, a rover designed for geology glimpsed an interstellar visitor. The image wasn't scientifically valuable in the way MAVEN's chemical data was. It didn't reveal new information about composition or structure, but it proved something important. That 3I Atlas was bright enough to be visible even from ground level, even through an atmosphere, even with equipment never intended for this purpose. 3 spacecraft at Mars, 3 completely different views: HiRISE's pixelated sphere, MAVEN's ultraviolet chemical maps, Perseverance's faint smudge through Martian atmosphere. And scientists were beginning to realize that this pattern would continue as they examined data from spacecraft farther away. That every mission would contribute a different piece of understanding, and that assembling those pieces into a coherent picture would require rethinking assumptions about what it means to observe something in space. The asteroid hunters were about to prove that point even more dramatically, capturing details from distances that seemed impossible. While Mars spacecraft had proximity working in their favor, 2 other NASA missions faced an entirely different kind of challenge. Lucy and Psyche are asteroid explorers, spacecraft traveling through the solar system on multi-year journeys to study rocky bodies that orbit far from Earth. Their instruments are designed for close examination, for detailed analysis when they finally arrive at their targets. They were never intended to observe comets, especially not from the vast distances that separated them from 3I Atlas in September. But both spacecraft had something valuable: clear lines of sight and mission teams willing to try something ambitious. So despite the enormous distances involved, despite instruments not optimized for this kind of observation, Lucy and Psyche turned their cameras toward the interstellar visitor and attempted what seemed nearly impossible. Psyche went first, On September 8th and 9th, it acquired observations of the comet over an 8-hour period. The distance was staggering, 33 million miles. To put that in perspective, that's roughly the distance from Earth to Mars at some points in their orbits. Observing a comet from that far away is like trying to identify a snowflake from across an entire city. The comet was extraordinarily faint, barely distinguishable from the background stars surrounding it, a tiny point of light that could easily be mistaken for anything else without careful analysis. Psyche's images don't look impressive to the casual observer. Small, faint, unremarkable. But to scientists tracking an interstellar object's path through our solar system, they were invaluable. By capturing the comet's position at multiple times, Psyche's team could refine orbital calculations. They could improve predictions about where 3i Atlas would be days or weeks later, helping other missions plan their observations more effectively. This wasn't about capturing beauty or revealing structure. It was about providing precise positional data that other teams could use. Then Lucy attempted something even more audacious. Between September 15th and 17th, Lucy turned its camera toward 3i Atlas from a distance of 240 million miles. That's more than twice the distance between Earth and the Sun. That's farther than Mars is from Earth at its farthest point. At that range, 3i Atlas wasn't just faint. It was nearly invisible, a signal so weak that a single image would show almost nothing useful. So Lucy's team employed a technique called image stacking. They captured multiple exposures, then aligned and combined them using software. By stacking images together, they amplified the faint signal of the comet while reducing random background noise. It's a method commonly used in amateur astrophotography, but applying it to a spacecraft observation millions of miles from Earth, tracking an interstellar object moving against the stellar background, required precision and patience. The result justified the effort. Lucy's stacked image actually revealed detail in the comet's coma, and even hints of a tail. From 240 million miles away, a spacecraft not designed for comet observation managed to capture structural information that other, closer missions had missed. This was remarkable not just for what it showed, but for what it proved about capability and adaptation. Lucy was approaching the outer limits of what's physically possible for observing such a faint target. Yet through planning, timing and technique, the mission achieved something that shouldn't have worked. But now compare these observations with what the Mars spacecraft captured. Psyche showed positional data, faint points of light that confirmed location, but revealed little else. Lucy showed structure through stacking, a processed composite rather than a direct photograph. HiRISE showed a pixelated bright coma. MAVEN showed chemical composition. Perseverance showed a smudge through atmosphere. 5 spacecraft. 5 entirely different representations of 3i Atlas. Not variations of the same image, but fundamentally distinct types of observation that emphasized different properties, revealed different aspects, told different stories, and the campaign wasn't finished yet. NASA's asteroid hunters proved something crucial during this effort. They demonstrated that missions designed for completely different purposes, traveling toward completely different destinations, could adapt their operations and contribute meaningful data to a coordinated campaign. They showed that distance doesn't automatically mean defeat, that technical limitations can sometimes be overcome through creativity and persistence. But they also revealed something about the nature of observation itself, because when you change the instrument, when you change the distance, when you change the method of capture and processing, you don't just get a different quality of image, you get a different kind of information entirely. Lucy's stacked images told a story about large-scale structure that close-up pixelated views couldn't. Psyche's positional data provided trajectory information that no amount of chemical analysis would reveal. Each spacecraft was answering a different question, even though they were all pointed at the same object. And as more missions reported their findings, this pattern would become impossible to ignore. The differences weren't mistakes or failures. They were features of how science actually works, how knowledge is built from multiple incomplete perspectives that must be assembled into coherent understanding. The solar observatories were about to add yet another dimension to this growing puzzle, capturing 3i Atlas in regions of space where no other instrument could see it, revealing aspects of its journey that would otherwise be completely unknown. Their observations would fill critical gaps in the timeline, tracking the comet through the most dangerous part of its passage, the region closest to our Sun where heat and radiation reach their peak. And once again, what they saw would look nothing like what anyone else had captured. In late September and early October, something happened that Earth-based telescopes simply couldn't handle. 3I Atlas passed near the Sun from our perspective, moving through a region of sky so bright with solar glare that ground-based observation became impossible. No matter how powerful your telescope, no matter how clear your skies, you cannot see through the overwhelming brightness of the Sun. That light drowns out everything nearby, creating a blind zone where objects simply vanish from view. But NASA had spacecraft positioned exactly where they needed to be. Missions designed to stare at the Sun all day, every day, without flinching. And those missions could do something Earth-based astronomers could not. Track 3. I-Atlas through the solar glare, maintaining continuous observation during a critical period when the comet was at its most active. STEREO, the Solar Terrestrial Relations Observatory, has been watching the Sun since 2006. Its purpose is studying solar wind, coronal mass ejections, and the structure of the Sun's outer atmosphere. It observes regions of the sky close to the solar disk, areas that most telescopes avoid because the light is too intense. From September 11 to October 2nd, STEREO tracked 3I Atlas as it moved through this blind zone, capturing images that showed the comet speeding through space at over 130,000 miles per hour. STEREO's observations were stacked together to show motion across multiple days, revealing the comet's path through a region no one else could see. This wasn't about beauty or detail. It was about maintaining the observational record, ensuring there were no gaps in the tracking data, confirming that scientists knew exactly where the comet was, even when Earth-based telescopes lost sight of it. SOHO joined the effort. The Solar and Heliospheric Observatory, a joint mission between NASA and the European Space Agency, has been studying the Sun since 1995. Over its decades of operation, SOHO has discovered thousands of comets, more than any other spacecraft in history. Most of those discoveries were accidental, comets that happened to pass through SOHO's field of view while it was monitoring solar activity. SOHO observed 3I Atlas, capturing it in positions where Earth-based astronomers remained completely blind. Then Punch contributed its observations. The polarimeter to unify the corona and heliosphere launched earlier in the year, making it one of NASA's newest solar missions. From September 28 to October 10th, Punch revealed the comet's tail during its observations near the Sun. This was historically significant. For the first time, NASA's heliophysics missions, which have observed thousands of solar system comets over decades, were purposefully tracking an object confirmed to originate in another star system. Think about what that means. Missions built to study our Sun, our star, our source of life and energy, all turning their instruments towards something from beyond. It was unprecedented within an already unprecedented campaign, a crossing of boundaries between different types of space science that normally remained separate. But once again, the observations didn't match what other spacecraft were seeing. STEREO captured motion and trajectory across multiple days. SOHO focused on position relative to the Sun during a critical blind period. Punch revealed tail structure that other missions had barely glimpsed. Each mission's instruments were optimized for solar observation, not comet analysis. They adapted, but the data they produced was fundamentally different in character and content from what Mars spacecraft or asteroid explorers had captured. 8 spacecraft now, 8 different views, 8 different kinds of data, 8 different perspectives on the same object. The solar observatories filled a critical gap in the observation timeline, maintaining continuous tracking during a period when 3I Atlas would otherwise have vanished from human view. They proved that coordination across mission types isn't just useful, it's essential when studying objects that move through changing conditions. But they also reinforced the growing pattern. Every spacecraft was revealing a different aspect of 3I Atlas, emphasizing different characteristics, telling a different part of the story. And scientists were beginning to understand that this wasn't a problem requiring solution. It was revealing something profound about how observation works, about the relationship between our instruments and the reality they measure, about what it means to truly see something in space. The explanation was beginning to emerge, and it would challenge assumptions about scientific observation that had stood for decades. So why did every spacecraft see something different? The answer isn't mysterious once you understand what these instruments were actually doing, but it's far more fascinating than most people realize. It starts with recognizing what 3I Atlas actually is. This isn't a solid, unchanging object like a planet or an asteroid sitting quietly in space. It's a comet, which means it's dynamic, reactive, constantly evolving as conditions around it change. Comets are made of ice and rock, material that remained frozen for potentially billions of years as they drifted through the cold darkness of space. But when a comet approaches a star, when sunlight begins warming its surface, everything changes. Ice sublimates directly into gas without melting first. Dust trapped in the ice gets released, forming a cloud around the nucleus. Gases stream away, pushed by solar wind and radiation. The comet develops a coma, that fuzzy envelope surrounding the core, and often grows a tail stretching millions of miles behind it. All of this means that a comet is not one thing. It's multiple phenomena happening simultaneously. There's the solid nucleus, the icy core where most of the mass exists. There's the coma, the atmosphere of gas and dust surrounding that nucleus. There's the tail, or often multiple tails, streaming away in different directions. And all of these components behave differently depending on what you're measuring. Look at a comet in visible light, and you're seeing sunlight reflecting off dust particles in the coma. Look at it in ultraviolet, and you're seeing specific molecules glowing as they absorb and re-emit solar radiation. Look at it with infrared instruments, and you're detecting heat signatures from dust and ice. Look at it with spectrographs, and you're identifying individual chemical elements by the wavelengths they absorb or emit. Each method reveals something real, something genuinely there, but they reveal different aspects of the same complex phenomenon. The instruments themselves impose additional differences. HiRISE is an optical camera designed for high-resolution surface imaging. It uses short exposure times and narrow wavelength ranges optimized for photographing solid terrain. When it looked at 3i Atlas, it captured what visible light cameras capture, the bright inner coma where dust density is highest. The nucleus was too small to resolve at that distance, and the outer coma was too faint for the exposure time used. The result was a pixelated sphere not because the comet looks like that in any absolute sense, but because that's what HiRISE's specific capabilities and limitations allowed it to see. MAVEN's ultraviolet spectrograph operates in completely different wavelengths. It's not looking at reflected light, it's detecting electromagnetic radiation emitted by atoms and molecules as they're energized by solar wind. That's why MAVEN could map hydrogen and hydroxyl, why it could estimate chemical ratios and composition. It was seeing chemistry rather than structure, molecular activity rather than physical shape. Both observations are accurate, but they're measuring fundamentally different properties. Lucy and Psyche faced challenges that required image stacking, capturing multiple exposures and combining them to amplify faint signals. This technique works, but it produces composites, processed images that represent data from multiple moments averaged together. The final image isn't a direct snapshot, but a mathematical combination of several observations. It reveals structure that single exposures would miss, but it's a different kind of representation than a straightforward photograph. The solar observatories were tracking motion and position near the sun's overwhelming glare. Their instruments are built to handle extreme brightness gradients, using filters and coronagraphs to block direct sunlight while revealing dimmer objects nearby. What they captured was trajectory information, speed, path through space. Not detailed structure or chemical composition, but positional data during a period when no one else could observe. And Perseverance, attempting astronomy from the Martian surface with a geology camera, saw a smudge because that's all a fixed camera with a long exposure could capture, of a moving target through atmosphere from millions of miles away. Different instruments, different wavelengths, different distances, different techniques, different purposes. Every spacecraft saw something different because each was optimized for specific types of observations, built to measure different properties, optimized for different tasks that happened to be temporarily redirected toward the same target. But here's the crucial insight that transforms this from confusing to enlightening. Each observation was accurate. HiRISE really did capture a bright pixelated coma. MAVEN really did detect those molecular signatures. Lucy really did reveal tail structure through stacking. The solar observatories really did track motion through the blind zone. None of them were wrong. They were incomplete, certainly, capturing only aspects of a complex phenomenon. But within their capabilities and methods, they were measuring real properties of 3i Atlas. This is how science actually works when you strip away the simplified versions taught in schools. We don't point instruments at targets and receive objective truth. We build tools that measure specific properties, that respond to particular wavelengths or particles or electromagnetic radiation. Those tools return data about what they're designed to measure, and then we, human scientists, must interpret that data, understand its limitations, recognize what it reveals and what it leaves out. No single instrument tells the complete story. That's why multi-wavelength observation campaigns are valuable. When you combine HiRISE's visible light imaging with MAVEN's ultraviolet chemistry, with Lucy's structural observations, with Stereo's trajectory tracking, you start building a more complete picture. Not a single perfect image, but a multi-dimensional understanding that includes physical structure, chemical composition, motion through space, and behavior over time. You learn that 3I Atlas has a coma extending across hundreds of thousands of kilometers, that its nucleus is small, probably just a few kilometers across, that it's releasing water vapor and carbon dioxide as it heats, breaking down into hydrogen and hydroxyl molecules, that it's moving at speeds that confirm its interstellar origin, that it develops tail structure similar to comets born in our own solar system. You learn that despite traveling from another star, despite potentially forming under different conditions, it behaves like comets we've studied for centuries. And that similarity is itself profound, suggesting that the basic physics of ice and dust and sublimation works the same way regardless of where an object originated. NASA scientists emphasized this point in their November release. They addressed rumors directly, speculation that had been circulating during the observation period about anomalies and unusual behavior. The data, they said clearly, shows that 3I Atlas looks and behaves like a comet. The observations differ because observation methods differ, not because anything anomalous is happening, but there's something deeper worth recognizing. The fact that 12 spacecraft could all observe the same object and produce such visually distinct results reveals how much our understanding depends on perspective, on the specific tools we choose, on the questions we think to ask. It reminds us that knowledge isn't simple, that seeing isn't straightforward, that the universe doesn't reveal itself in a single glance, but must be examined from multiple angles using multiple methods before we can claim to understand what we're looking at. And it reminds us that interstellar objects, even when they behave exactly like objects from our own solar system, still challenge us in unexpected ways, forcing us to confront assumptions about observation and measurement that we didn't even know we were making. So what did we actually learn from this unprecedented campaign? What does all this observation, all this coordination, all these complementary perspectives actually tell us about 3I Atlas and where it came from? The answers are simultaneously mundane and profound, confirming expectations while revealing subtle details that only multi-spacecraft observation could provide. Start with composition, the fundamental question of what this object is made of. MAVEN's ultraviolet observations provided crucial chemical data by detecting specific molecules in the coma. Water vapor is present, breaking down under solar radiation into hydrogen and hydroxyl molecules. Both were detected and mapped across different regions of the coma, showing how the distribution changes with distance from the nucleus and exposure to sunlight. Scientists also measured deuterium to hydrogen ratios. Deuterium is heavy hydrogen, an isotope with an extra neutron that forms under specific conditions. The ratio between deuterium and normal hydrogen acts like a fingerprint, revealing information about where and when an object formed. Different regions of the galaxy, different types of stellar environments produce different deuterium signatures. While the data is still being fully analysed, MAVEN provided an upper limit for this ratio, narrowing down the possible origins and formation conditions of 3I Atlas. Carbon dioxide ice was confirmed through spectroscopic observations. Water ice is present and actively sublimating as the comet heats. And interestingly, a nickel signature showed up in spectroscopic data, similar to what was detected in 2I Borisov, the previous interstellar comet. This pattern suggests something potentially significant. Either interstellar comets naturally contain more nickel than our solar system's comets, or nickel is more readily released from their surfaces under solar heating. Either way, it might become a useful marker, something that helps identify interstellar origins in future observations. Size estimates remain somewhat uncertain. Hubble observations suggest a nucleus just a few kilometers across, but the exact dimensions are hard to pin down. HiRISE couldn't resolve the nucleus directly because distance and dust obscured it. Current estimates range from hundreds of meters to a few kilometers, which is typical for comets but frustrating for scientists who prefer precision. That uncertainty isn't unusual, though. Comet nuclei are small, dark, and buried inside bright comas of dust and gas. Getting precise measurements requires either very close flybys or extended observation campaigns with multiple methods. Speed is more certain. 3i Atlas is moving faster than any object gravitationally bound to our Sun, travelling at velocities that unambiguously confirm its interstellar origin. Stereo and other missions clocked it at over 130,000 miles per hour relative to the Sun. That speed is the signature, the proof that this object came from somewhere else. Objects bound to our solar system follow predictable orbital mechanics based on their distance and trajectory. 3i Atlas was moving too fast, on a path too hyperbolic, to have originated here. Brightness behaviour caught attention as the comet approached perihelion, its closest point to the Sun, which occurred on October 29th. As expected, it brightened dramatically. Closer proximity means more heating, more gas release, more visible activity. But the specific patterns of that brightening, the rate of change and variability, those details matter for understanding how this comet compares to others. Scientists are still comparing 3i Atlas's light curve to solar system comets and to 2i Borisov, looking for similarities and differences that might reveal subtle distinctions in composition or structure. So far, everything looks normal for a comet. That's both reassuring and slightly disappointing. Reassuring because it confirms that comets from other star systems follow the same physical laws as ours, that the universe operates consistently regardless of location. Disappointing because it means 3. Atlas probably won't reveal radically different chemistry or behaviour that would revolutionise our understanding. The tail appeared faintly in visible light images, showing the classic blue-green colour created by carbon-based molecules fluorescing under solar radiation. An ion tail formed, shaped and directed by solar wind, streaming away from the Sun in the direction determined by charged particle flow. Everything a comet should look like, behaving exactly as comet physics predicts. Shane Byrne from the HiRISE team captured the essence of what this campaign meant. Observations of interstellar objects remain rare enough that every attempt teaches something new, he said, and that's the crucial point. This isn't about discovering alien technology or strange anomalies. It's about studying material that formed around another star, in another system, under potentially different conditions. Even if 3i Atlas behaves like our comets, its chemistry might reveal subtle differences that tell us about its origin. The precise ratio of water to carbon dioxide, the abundance of specific metals, the isotopic signatures that trace formation conditions. These details help scientists understand how planetary systems form across the galaxy, how common certain processes are, whether the chemistry that led to life on Earth exists elsewhere. Justin Dagan from Maven put it simply, every measurement opens new understanding about interstellar objects. That's the value being delivered here. Not sensational headlines or revolutionary discoveries, just solid, careful, incremental expansion of human knowledge built on coordinated observation and meticulous analysis. But the campaign also revealed something about our capabilities as a spacefaring civilization. The fact that NASA could coordinate 12 separate assets, capture data across multiple wavelengths and vast distances, fill gaps in observation using missions designed for completely different purposes, and produce a coherent scientific picture demonstrates how far we've come. 30 years ago, we wouldn't have had spacecraft at Mars with instruments capable of this kind of observation. We wouldn't have had solar observatories positioned to track objects near the Sun. We wouldn't have had asteroid missions with enough operational flexibility to redirect their cameras millions of miles off course. We wouldn't have had the communication networks, the data processing capabilities, or the coordination structures to pull off something this complex. Now we do, and when the next interstellar object arrives, and statistically there will be others, we'll be even more prepared. We'll know which spacecraft are best positioned for different types of observation. We'll understand which instruments provide the most valuable data for answering specific questions. We'll have protocols for rapid response, for coordinating across missions, for ensuring that we don't miss opportunities the way we did with Oumuamua. The something different that each spacecraft saw isn't a problem that needed solving. It's a feature of how observation actually works, a reminder that reality is complex and multidimensional, that understanding requires multiple perspectives combined into synthesis, rather than single perfect viewpoints that reveal everything at once. 3. iAtlas came from another star system carrying materials formed in conditions we can only theorize about. It travelled through interstellar space for possibly billions of years before crossing paths with our Sun, and it gave us months to study it, to point every available instrument in its direction, to gather data that will be analysed for years after the comet itself has vanished back into darkness. That opportunity doesn't come often, and NASA ensured we didn't waste it. We need to address the rumours directly, because while NASA was preparing their data release, speculation was building to levels that demanded response. The delay caused by the government shutdown created a vacuum of information, and that vacuum filled quickly with theories, claims, and suggestions that range from plausible to absurd. Some people pointed to the delayed release as evidence that NASA was hiding something, that the images revealed findings too controversial or unusual to share immediately. Others claimed that inconsistencies in the data suggested anomalous behaviour, that 3I Atlas wasn't behaving like a normal comet should. A few voices went further, suggesting that the object might not be natural at all. Avi Loeb, the Harvard astrophysicist who previously proposed that Oumuamua might be artificial, made similar arguments about 3I Atlas. He pointed to what he described as anomalies in the comet's non-gravitational acceleration, suggesting these deviations from pure, gravitational motion could indicate something unusual about the object's nature or origin. Let's be clear about what non-gravitational acceleration actually means in the context of comets. When comets approach the Sun, solar heating causes ice to sublimate into gas. That gas doesn't just sit there, it streams away from the nucleus, creating what's essentially a tiny rocket thrust. This outgassing produces forces that slightly alter the comet's trajectory in ways that gravity alone can't explain. Astronomers account for this when calculating comet orbits. It's called non-gravitational acceleration, and it's completely normal, expected behaviour for any active comet. The question Loeb raised is whether 3I Atlas's non-gravitational acceleration is unusual compared to other comets. Most planetary scientists who specialise in comet physics are sceptical. The acceleration measurements are difficult to make accurately, because comets are fuzzy objects without sharp boundaries. Pinpointing a precise centre position for something surrounded by a cloud of gas and dust introduces uncertainties that can significantly affect calculations. Those uncertainties might not be properly accounted for in the analysis Loeb referenced, meaning the apparent anomaly could be measurement error rather than genuine unusual behaviour. The true non-gravitational acceleration is likely much smaller than claimed, falling well within the range of normal comet physics. But beyond that specific technical debate, NASA addressed the broader speculation directly and explicitly when they released the observations on November 19th. The data shows a comet, they said clearly. A comet that behaves like comets behave. It releases water vapour and carbon dioxide as it heats. It brightens as it approaches the Sun. It develops a coma and tail. Its chemical signatures match expectations. Its light curve follows models. Nothing about it suggests artificial origin or technology, or anything beyond natural comet physics. The image delays weren't covering up controversial findings. They were the direct result of the government shutdown that lasted from early October through mid-November. Public releases were halted across NASA during that period. Scientists could continue analysing data internally, but sharing information with the broader community had to wait until normal operations resumed. Once the shutdown ended, NASA moved quickly to organise a comprehensive release, a public event, mission-by-mission data breakdowns, an image gallery showing every observation, full transparency about what they'd found. The truth is less dramatic than conspiracy theories suggest. 3I Atlas is a comet, an extraordinary comet because it came from another star system, because it travelled unimaginable distances to pass through our neighbourhood, because it gave us an unprecedented opportunity to study interstellar material up close. But still a comet, following the same physical laws, exhibiting the same behaviours, made of the same basic materials. Why do these rumours gain traction despite evidence to the contrary? Partly because interstellar objects genuinely are rare and mysterious, triggering natural human curiosity about what they might represent. Partly because phrases like, "from another star system," prime our imaginations, making us expect something extraordinary beyond just chemistry and physics. And partly because some scientists, like Loeb, are willing to publicly entertain unconventional hypotheses, giving those ideas credibility they might not deserve based on current evidence. There's value in considering alternatives, in not dismissing possibilities too quickly. Science advances by challenging assumptions, by asking uncomfortable questions, by entertaining ideas that conventional wisdom rejects. But there's also value in proportionality, in not elevating unlikely explanations above straightforward ones when the evidence points clearly in one direction. Right now, every piece of data from 12 different spacecraft and multiple ground-based telescopes points to 3I Atlas being a natural comet. Its composition matches comet models. Its behavior follows comet physics. Its appearance resembles other comets. Until evidence emerges that genuinely contradicts this interpretation, that's the conclusion science supports. The 12 spacecraft observation campaign, far from revealing anomalies, actually reinforced this conclusion. Each mission captured what its instruments were designed to capture, and all of it combined into a coherent picture of a comet passing through our solar system. Different instruments produced different data, yes, but those differences arose from observation methods, not from anything anomalous about the object being observed. NASA was clear and direct in their messaging, explicitly rejecting claims of artificial origin or unexplained behavior. They presented the evidence, explained the findings, and stood behind the scientific consensus that 3I Atlas is exactly what it appears to be, an interstellar comet giving us a rare opportunity to study material from beyond our solar system. The observations will continue. An analysis of the data will extend for months or years as scientists extract every possible insight from what was captured. But the fundamental conclusion is already clear and unlikely to change. The observations aren't finished. 3I Atlas is still moving through our solar system, and NASA spacecraft are still watching, still gathering data, still adding to the comprehensive picture being built from months of coordinated effort. The comet made its closest approach to Earth on Friday, December 19th. At roughly 170 million miles, it wasn't particularly close by astronomical standards, about twice the distance between Earth and the Sun. But it was close enough for continued observation, close enough that ground-based telescopes and space missions could maintain tracking, adding to the timeline, of data that stretches from initial discovery through final departure. James Webb Space Telescope observed 3I Atlas in August, and has additional observations planned for December, and those observations represent potentially the most detailed examination yet. Webb operates primarily in infrared wavelengths, which gives it unique capabilities. Infrared can penetrate dust that blocks visible light, revealing structures and details that optical cameras miss. Webb can analyze chemical composition with extraordinary precision, detecting molecules and isotopes that other instruments simply can't see. Scientists expect Webb's data to provide the most comprehensive composition profile of any interstellar comet we've studied. If subtle differences exist between interstellar and solar system comet chemistry, if formation conditions around another star left chemical fingerprints that distinguish this visitor from objects born here, Webb has the best chance of revealing them. Beyond December, 3I Atlas will continue moving outward. It will pass Jupiter's orbit in spring of 2026. Cooling as it travels farther from the Sun, its activity gradually decreasing as solar heating diminishes. Eventually it will fade from view, becoming too faint and too distant for even our most sensitive instruments to track. But until that happens, observation will continue. Every additional data point refines orbital calculations, helping scientists trace backward to determine where this comet came from, and forward to predict its path through interstellar space. This extended campaign represents something unprecedented in astronomy. For the first time, humanity is tracking an interstellar object across its entire passage through our solar system, from initial discovery through closest approach to final departure. We missed that opportunity with Oumuamua, discovering it too late and watching it vanish before we could mobilize resources. We had limited time with 2E Borisov, studying it intensely, but always aware that our window was closing. But with 3I Atlas, we've been watching since discovery, and will continue watching until it becomes physically impossible to detect. The coordination itself stands as an achievement worth recognizing. Mission planners from 12 different spacecraft, working across institutional boundaries, sharing observation windows and data and strategies. Scientists from multiple fields, analyzing different aspects of the same object, building understanding collaboratively. This is modern astronomy functioning at its best, demonstrating what becomes possible when resources are coordinated and expertise is pooled, and the lessons extend beyond this single comet. We've learned that our existing spacecraft fleet, even missions designed for completely different purposes, can adapt to study interstellar objects. We've learned which kinds of observations provide the most valuable data, which instruments are worth prioritizing, which wavelengths reveal the most information. We've learned that coordination is possible even across missions with different goals and different management structures, that when opportunities arise, the system can respond effectively. When the next interstellar object arrives, and statistically there will be others discovered as our detection capabilities improve, we'll be ready in ways we weren't before. We'll know which spacecraft to mobilize immediately. We'll understand which types of observations to prioritize. We'll have protocols for rapid coordination, for sharing data efficiently, for ensuring that every available resource contributes to comprehensive study. The something different that each spacecraft saw isn't a failure of technology or coordination. It's the reality of how observation works, how different tools reveal different aspects of complex phenomena, how understanding emerges from synthesis rather than from single perfect viewpoints. HiRISE showed structure in visible light. MAVEN revealed chemistry in ultraviolet. Lucy captured morphology from extreme distance. Solar observatories tracked motion through blind zones. Each perspective was incomplete but accurate, partial but genuine. Combined, they create understanding that's richer and more complete than any single observation could provide. That's the lesson worth carrying forward, the insight that transforms this from a story about one comet into a demonstration of how science builds knowledge from multiple, imperfect sources assembled into coherent synthesis. 3, I-Atlas came from another star, travelled unimaginable distances through the cold darkness of interstellar space, entered our solar system carrying materials formed in alien conditions, and gave us months to study it with every tool we could bring to bear. It approached the sun, heated and brightened, released gases and dust, developed a coma and tail, behaved exactly as comet physics predicts, and now it's leaving, heading back out into the darkness, following a hyperbolic trajectory that will carry it away from our sun forever. When it vanishes from our last telescope's view, it will leave behind the most comprehensive dataset ever collected on an interstellar object, observations that scientists will analyze for years, insights that will inform our understanding of how planetary systems form and what materials exist beyond our solar neighborhood. That's the legacy of this unprecedented campaign. Not sensational discoveries or revolutionary findings, just careful, thorough collaborative science demonstrating that we're learning, that we're improving, that we're ready for whatever visitors come next. So where do you stand after seeing all this evidence? Do the differences between spacecraft observations suggest something we're missing? Or does the scientific explanation satisfy your questions about why each mission saw something distinct? Drop your thoughts in the comments and make sure you're subscribed, because when James Webb's December observations are released, we'll be analysing what they reveal about 3I Atlas's chemistry and comparing it to everything we've learned so far. Until then, keep looking up.